Yeah, good evening all. So in the meantime till the other students join, so just to give an introduction of this course, so this course is essentially Computational Fluid Dynamics of Incompressible Flows. So we will discuss on finite difference and finite volume methods to solve the Navier-Stokes equations. Intended audience are generally undergraduate and postgraduate students and faculty members as well. Basic prerequisites are you need to have a basic idea of what the fluid mechanics equations were, that you can brush up on those topics. Those will not be covered in this particular course. And about myself, I'm a Paymar scholar from Department of Mechanical Engineering in IIT Madras, and my research deals with working on computational fluid dynamics for understanding thermal and fluid dynamics of flows inside buildings. And regarding these live sessions, will happen every Saturday from 5 to 7 p.m. and the link will be circulated to all the enrolled students from the NPTEL website. And all the sessions will be recorded and you can access them on my YouTube channel. This material will be uploaded on the Google Drive folder, which you can access from the course website itself. And if you have any queries regarding the live sessions, you can send an email to me at me22t400@sml.iitm.ac.in. If you have any queries other than the ones that we discussed in the live sessions regarding the course or an enrollment exam registration or anything of that particular sort, you can raise those queries on the discussion forum. So this is your course website. You can find all the assignment questions that we are solving here, the recorded sessions YouTube channel, and the Drive folder you can access from here. And the discussion forum you can access from the Q&A part here, where you have to sign up for the Google group and then you'll be able to access the discussion forum. Last week we discussed on applications of CFD as a broad overview, and we kind of just brushed up on some governing equations, continuity, momentum, and the energy equations. We also discussed on species transport and the different kinds of boundary conditions that we usually encounter in CFD. This week we will be discussing partial differential equations, the kinds of partial differential equations, elliptic, parabolic and hyperbolic equations, and how they are relevant for this particular CFD. And the assignment of this week is also focused on, okay, if you were given a partial differential equation, how to identify which type of equation it belongs to. That is the main object or main takeaway from this particular week. Before going into or maybe I'll go through the summary, or if you have any questions, please unmute yourself or you can type in the chat box. So if you have already gone through the lecture videos, do you have any questions on them from the lecture, or any clarification in the assignment problems or anything of that sort? We can discuss them first. Yeah, if you do have any questions, I can give you a brief summary of the lecture videos, and if you do have any questions, please feel free to unmute yourself or you can also type in the chat box. So the whole idea is, when we know that when we have a physical quantity of interest which varies as a function of several variables, then we define something called a partial differential equation, where let's say phi's are variable of interest which varies with respect to x and y. Phi xx is basically the derivative of it with respect to, like we first define phi x as a partial derivative, which essentially means the rate of change of phi with respect to x provided y is constant. If you have a general second order PDE, here second order refers to the order of the highest differential term in this, then what this tells us is the characteristic equation is given by this particular form, where dy dx is b plus or minus square root of b square minus 4ac by 2a, where this is our discriminant. Depending on the value of the discriminant, we can decide whether it is which type of equation it is. And how is that physically relevant is, if this particular value is positive, then we have real solutions for dy dx. So those are called the characteristic lines. And what we can do once we know the characteristic lines is, there is a method called method of characteristics, which helps us to convert this PDE into an ODE, which we will be able to solve later. So knowing the type of equation it is, we will choose the algorithm accordingly. So to give you an example, You can see the water ripples in this particular video. Observe the wave front that is moving over here. If we want to model this phenomenon, essentially we want to understand or we want to predict the height of the water wave as it travels as a function of time. So if that is our variable of interest, so which type of equation do we use depends on the mathematical characteristics of this equation. Here the important parameter here is if you are sitting on the wave, then according to you, before and after the wave you didn't observe anything. So which means that this is information is actually propagating radially outwards, and any time when you are sitting on the wave, you would observe everything else to be at static. So these kind of motions are described by something called a hyperbolic equation, which comes only when you have distinct values of d by dx. It will be easy if you were to think in terms of a 1D equation, where instead of y we are having the x coordinate, and x in terms of we are having a time coordinate or something, some variable where x represents a time and y represents your spatial location. Then this would be a straight line if you were to draw in the space versus time graph. So this kind of PDEs where you have a definite direction for the information flow, we categorize them as hyperbolic, and hyperbolic equations are solved in a specific way. And then there is another kind of problem where we have something like this. There is some dye, and you can see how the dye is kind of spreading away. So how is this different from the previous one? This versus this, if you were to observe. Here the waves are traveling. Once the wave moves from one place to another place, the information is propagated. So whatever is the source of disturbance, the disturbance is moving away from the wherever it is originally located. Here also something similar happens. There is a disturbance at the center. It also moves away, but it kind of goes in all the directions equally, and it doesn't have any specific way. That, for example, if there is a point here that also knows that every point in this domain knows that something is happening at that there is a disturbance at the center, and that disturbance is kind of propagating in all the directions at the same time. So put it in other words, we were to say the domain of influence here is any disturbance that is causing here has been felt by every other particle in this vicinity. Then we will be calling that as a parabolic phenomenon. This happens when we have b square minus 4ac, or the discriminant, to be equal to 0. Is the difference between these two phenomena clear? So, okay, can you give an example of an elliptic problem? Elliptic is the one which is not either of these, so it should be a scenario where I have the discriminant to be less than 0. Two D Laplace equation on a 2D plate is an elliptic. So once we have the Laplace equation, it is an elliptic equation. Any other example? So the main difference between this phenomenon and other one is in elliptic equations we have information propagating in kind of instantaneously. So there is no something like time, like I cannot show you a video where it kind of propagates or something. If we say that it is propagating in some way, then it is either hyperbolic or parabolic in nature. So the one example that is pointed out is the 2D Laplace equation, that is a steady state equation. So any disturbance felt in any disturbance anywhere has to be felt everywhere instantaneously. This also happens in something which we will discuss later inside the Navier-Stokes also with the pressure term. We have a pressure Poisson equation. Once we will see that later. So what that means is if there is any velocity changes, because of that the pressure will also get kind of affected instantaneously for incompressible flows, which we will see later, but the idea is the same. So these are some problems from previous year questions. You can quickly answer them. The lines along which a partial differential equation reduces to an ordinary differential equation are called as. So as I said, these are the lines along which, these are the characteristic lines. So once you know the characteristic lines, you can solve the differential equation along that particular lines. So maybe let me ask few more questions here. So let's say I have a parabolic equation for which, or let's take an example of a parabolic equation. Something like this. So is this parabolic? If you were to compare this with the second order form that I have shown before, value of A is 1, B and C are 0. So B and C are 0. So this term discriminant becomes 0. So this is parabolic in nature. So what will be the characteristic lines for this equation? You can use this equation here. So this should give me the characteristic line. So instead of y, we are having the like we do not have y here. So this will be d. And b here is 0. And this is 0. So if I were to draw it on an axis with the so something like this, where I have t on my y-axis, and let's say I have x on my x-axis. So if the t versus x, dt dx equal to 0, so that would be a straight line. So what does this physically signify? U equals to constant. No, u is this particular variable, like we do not have the solution yet. So when we are trying to classify PDEs, what we are trying to do is, without actually solving the PDE, just by seeing the coefficients, what can we determine, what can we understand about the nature of the phenomenon that this PDE is trying to represent. So we are not trying to solve this equation now, which we will see next week, how to solve this equation using finite difference, we will see next week. So this week is about, without actually solving, just by seeing the equation, what can we infer about the physical phenomenon. So in this particular case, we are able to say that dt dx equal to 0, like we were able to draw something called state space, or basically t versus x plot. So this has some significance. So if we were to try to understand this particular one, what we are trying to say is, if there is any disturbance that is happening, like the statement that I made before, that information propagates along one direction or multiple directions, or it travels instantaneously. All those statements, how do I make those statements from plots like this? So I got an equation which says from the characteristic equation, I got to know that dt dx equals to 0. So from that equation, I was able to make this plot. So from this, how will we reach the conclusion that information is traveling at a given speed, or it's traveling in all directions or something? Disturbance is constant throughout. We cannot comment directly on the disturbance, because the strength of disturbance is the variable that we are trying to solve, u here. We are not solving the equation directly, so which means I do not know whether the functional form. So the statement u equal to constant or disturbance is constant are kind of equivalent. So we are not trying to solve for the value of u, we are trying to understand the nature of how this propagates. So if there were some u, we do not know what the value is. What this says is at all the x's, at any given time, it has an influence throughout all the x, since dt dx equal to 0. This line says where the influence of that particular disturbance is happening. So if this were a hyperbolic equation, let's say I have a different equation, something like the wave equation that it actually goes in a reverse way, but let's say for the sake of this, I just put this constant to be 1. Let's say I have an equation like this. Can you check whether this is hyperbolic or not? And check and confirm yourself that this is hyperbolic. Yes, hyperbolic. So now for this, what will I get the expression for dt dx? So if I were to draw the same plot as before, if I were to draw the same plot as before, how would that look like? Here dt dx will be I'll have dt dx to be plus or minus 1, and if I were to draw that on the same plot here, let's use plus 1 or minus 1, something like this. What this means is, at any given x, at any given location in my physical domain, or at any given time, or if you say at any given time, there are only 2 positions in the physical domain that are actually getting influenced, which is what we are seeing in the ripple video that before. So if you see in this video, if I kind of freeze it at any point of time, the influence is like this is kind of 3D one, but if you were to kind of cut a line, like draw a line on this, and see there are only 2 points where the wavefront is hitting, like any given wavefront from where the original disturbance has started, it touches at only 2 points, and those are the only 2 points that are getting influenced by the disturbance that was there previously. But if you were to look at the parabolic example, and let's say I freeze it at any given time and kind of draw a line like only along one dimension, x direction, we will see that all the points along that x, it's not like a one point, there are many points at any given time that are getting influenced by the disturbance that was there at an initial condition. Like at t equal to 0, if there is a disturbance, the effect of that at a different time is kind of spread out along multiple x values. So that is what this particular diagram is showing, like if I were to simplify it. So this is the parabolic one, which says that dt dx equal to 0, and this is the hyperbolic one where there are 2 different points at it. Like if it were 3D or 2D, then you will have surfaces instead of these lines, but the essential idea remains the same. So these are called the characteristic lines. So you can do some transformations so that instead of solving the equation in your original domain, you will solve the equation in the transformed coordinates. So in this particular form, instead of using this x and t coordinates like this, I can choose the red lines as my coordinate axis. If I do that, then that will kind of lead to some simplifications. Anyway, since we are not dealing with analytical solutions, we will not go into that. But this is something that will be useful later, which we'll use later once we solve hyperbolic equations. That comes in like week 6 or something. But I think the concept of characteristic lines is clear. And now as you can see, like once I am along a characteristic line, it's like if you are only along the x-axis, then you know that there is no effect of t on that. So which means, as we initially started out in partial differential equation, we assume that a given variable is dependent on 2 or 3 independent variables, like multiple independent variables. But if we are in a characteristic line, something like this, then it is only one variable that we are independent on. Like it doesn't depend on any other one. These are kind of orthogonal in nature. So what that means is the PDE is actually reduced to an ordinary differential equation. So that is what this particular question tells us. Like if you go along a characteristic line, then the PDE actually reduces to an ODE. So you can say that change is actually dependent on only one variable instead of the other ones. I think the intuition is clear. Yeah, now this one should be straightforward. Which of these apply to parabolic equations? How many characteristic lines do parabolic equations have? One, yes. They have one real characteristic line, and that is the one that we have seen here. So these are kind of, the two roots are becoming one. Two characteristic lines are for hyperbolic and imaginary are for the elliptic problems. Yeah, now these are two different terminologies. Which of these characteristics apply to hyperbolic equation? So now we have two other terms that is just for your exam purpose. You have something called domain of dependence and domain of influence. So what do you think this is like the names are kind of intuitive. So for a hyperbolic equation, which one of these do you think happens? Finite domain of dependence and infinite domain of influence, finite domain of dependence and finite domain of influence, no domain of dependence and no domain of influence. So whenever I say there is a dependence and an influence, there is something inherently that I am assuming that there is a causality associated with it. So there is something that is happening before that is causing something that is happening at a later point of time. So this causality is only happens in hyperbolic equations and kind of parabolic. So once you have an elliptic equation, like the steady state equation that you gave an example before, then we do not have this causality in picture. So there we have the entire domain of dependence and influence. So here for hyperbolic, it's both are finite. Okay, from here on it's more about using the discriminant analysis to answer these questions. What is the nature of this partial differential equation? So maybe let me ask a few more questions. So let's say you are given some differential equation which has so many variables. So how do you know like which variables to choose for x or y, or can it be anything, like you can arbitrarily choose anything? Let's say here there are only two variables, x and t. It will depend on the sign of beta. So what are the values of a, b and c? In this particular case, this is the x coordinate, so this is your beta. B is 0, C is 0. So if I were to calculate my discriminant, that will be 0 minus beta times four, right? It will again become 0. It's like it doesn't actually depend on the value of beta in this particular case. You have to only consider the coefficients of the highest derivative. Hope that is clear. This is the one that you are saying. So if it is parabolic, all you have to do is solve this equation and get the value of alpha. They're more of practice problems. You can quickly solve them. Okay. Yeah. Now we have the compressible flow equation given by the one that is shown here. When does it become hyperbolic? So all these problems are kind of similar. Once you know what the discriminant is, what the characteristic lines are, then this becomes simple. And let me kind of ask another question before going to the problem. If you see here, there are like multiple things happening here. Of course, there are multiple waves here. So the one that I said, that information like if you draw a line at any point of time, there are multiple points that are getting affected by this. So is this purely hyperbolic, or do we have parabolic also in this? Like whatever we understood from the example that I told, if I draw a line here and take all the points where we have if I draw a line along this one and take all the points wherever this influence is happening, so if there are only like 2 points, then it is a hyperbolic. That was what we were deciding. If it was like there are multiple points like all throughout, then I call it a parabolic kind of thing. So you can see here disturbance is kind of everywhere. So why do we say that it is still hyperbolic? Is the question clear? At a particular instant, the circle is intersecting at only 2 points along the x-axis. Yes, but there are multiple circles also. That is because of the second effect. Like energy is getting continuously added and you are having multiple. So in reality, what happens is, depending on the viscosity of the fluid, like affected by the previous one. Yes. So depending on the viscosity of the fluid, there will always be diffusion inside. But for most of the, like depending on what you are trying to model, so if your objective is to understand like the majority of the energy is kind of carried by this wave itself, and you are trying to understand how these waves kind of interact, etc., then you can consider a hyperbolic equation to model this phenomenon. But let's say you have some viscous fluid, then the dissipation might also be important. Then you might have to consider a parabolic. But if you consider the Navier-Stokes equation, let's say we take the full Navier-Stokes equation. So what kind of equation is Navier-Stokes? Let's say the momentum equation, or like let's take only the 1D form. So if we just take the 1D equation, so we have the unsteady term ut, second order I was trying to classify it in one of these things, elliptic, parabolic, or hyperbolic. Yeah, it's a second order. Some pressure term. For now, let's not take the pressure gradient term. So you have some diffusion term, something of this form. So is this parabolic, hyperbolic? What kind of equation is this? there is one major difference between this equation and the form that I have shown before, this one. What is that? Both are second order equations. This is also kind of homogeneous in the sense that we do not have this one, but what is the major difference? Parabolic. So if I were to add one more term, the pressure gradient term also, let's call it Px. Then this becomes a little more complex because you also have to consider, like, this is one equation and two unknowns, so you cannot simply say from it. You need one more equation for the pressure, which we will see later. That will be an elliptic equation. Pressure equation will be something like the Poisson equation, so it will be something like Pxx equals to something which we will discuss later. So because we have u is just only one equation, so we cannot solve two unknowns from one equation. The other equation will be something in terms of p. So this will be an elliptic equation and this will be a parabolic equation kind of thing. So that will be the combination that we will be solving. So the point I am trying to make here is depending on the form that you are trying to solve. So if you are solving a problem where the changes in, like, the pressure gradient is kind of negligible, and you know that the problem will actually you do not have to consider the transients are not that important in that particular problem, then you will neglect this term and you will treat the problem as an elliptic and you use an elliptic solver. But if you know in some problems the transients are important, then you solve in this particular way. In some problems, like the wave here, this is a phenomenon that is happening in the fluid, but you know there is a wave and you know that this is actually hyperbolic in nature. So then you need to consider your governing, like your model should be a partial differential equation which is hyperbolic in nature. So the choice of model will depend on your, like, this model has these particular characteristics. So depending on the phenomenon, you choose a correct model, and each kind of this model will have a different kind of solver. So there will be a solver that is suited for elliptic problems and parabolic and hyperbolic problems separately. Using inconsistent solvers for inconsistent phenomena gives you inconsistent results. So the main takeaway from this and how this is related to the CFD course is identifying the type of equation and seeing whether it fits to your particular problem or not. Coming back to the problem, so this is per se, this is a general equation, this m is the Mach number. So when does this become hyperbolic? P is 0. M greater than 1. So the same equation, depending on the Mach number, it either becomes a hyperbolic equation, or what happens if m is less than 1? If m is less than 1, then this becomes negative and it becomes an elliptic equation. So depending on the value of Mach number, it can either become a hyperbolic or an elliptic equation. So there will be some phenomenon like this where the governing equation you take which changes depending on this. So which means the type of solver you have to use should also change accordingly. Let's go to another equation. Let's say we have an equation of this particular form. So how is this equation different from the original standard form that I have shown before? This is the equation that we have here, and the one that I am referring to is this one. When I am discussing y is a variable, yes. So I didn't say what the coefficients were previously. I didn't mention whether the coefficients have to be constants or they have to be variables or something. So if they are constant, then it is kind of simplified. It's a linear problem. Now we have a nonlinearity here. Nonlinearity in the sense that the coefficients are also functions of the independent variables that you are trying to solve. So when will this equation be elliptic? Again the same discriminant. So for elliptic, should it be greater or less than? Less than 0. So that means y should be greater than 0. So you can see again here, this is a problem where again this is also very similar to the previous one. Different locations you have different kind of nature. So there can be physical phenomena like this. Now comes an interesting set of equations. So instead of like previous all the ones, we have just one variable. Now we have two different variables, u and v. So how do I identify the class of system of equations here? Or where do things like this happen? Let's take the 2D Navier-Stokes equation along with the continuity equation. Like we have three variables, the velocities and the pressure. So the three variables, like if you take the 2D Navier-Stokes equation, we have three variables, u, v and p. So I have three equations, which is continuity, x and y momentum. So these three equations together is when you decide whether the system is hyperbolic, parabolic or some elliptic, or which kind of system it is. You cannot just take the continuity equation and say that if you just take the continuity equation, it will be ux plus vy equal to 0. If you just take this equation and you say that okay, there is a, b, c all are 0, so this is parabolic in nature, is something that we do not do. You have to consider our entire system together and then comment on that system, because all those three equations combined together describes your physical phenomenon. So if these two equations taken together, which kind of system this belongs to? So how do I decide when I have something like this? So you define a new variable capital U, which is a vector kind of thing, or you can put it as a matrix, whichever way you are convenient. And then you write the governing equation in terms of that, where the governing equation will be in terms of u t plus some constant times ux equal to 0, where A is actually a matrix now. How will the matrix look like? In the first equation, we do not have any term for del u del x, so the first coefficient will be 0. Second coefficient will be for the v, the next coefficient for u, and the last coefficient for this. It looks something like this. So if you were to multiply this, this will be the term for del u del x, this is for del v del x, this is again del v del x, del u del x term and del v del x term. So ux is basically, let me just write that also here. So when we write this, ux is basically this. So you can multiply these equations and get the original equation back. So now what do we do from here? How do we apply the previous analysis to this problem? So what happens when we have a vector instead of a scalar? And one more distinction here is, what is the order of this equation? So each equation is essentially a first order equation. So let's say, can I convert this into a second order equation? So these are basically two first order equations. So can I combine this and make them into one second order equation? So if you have gone through the lecture videos, so how did we come with, how did we start from here to here? Like how did we derive these characteristic equations from the second order equation? Or let me put it in a simple way. Let's take these two equations. Can I do something here to convert these two equations into one second order equation? Any kind of operation that I can do, differentiate, and then if you were to differentiate, how would that be? So differentiate first equation with respect to x. So let's say the first equation derivative with respect to x, differentiate first with respect to y and second with respect to x, and then do addition or subtraction. But still that wouldn't solve the problem, right? Okay, can you do the transformation and tell me the final equation, the second order equation that you will be getting? You can wait for a couple of minutes so you can give it a try. These are the equations. Yeah, okay, so you got an equation in terms of utility and this one. So what is that equation tell you? Is that equation hyperbolic? And what is the assumption that you made when you arrived at that particular equation? So you have done derivative of first equation with respect to t, and then second equation with respect to x, and then you substitute it back, right? So if I were to take the derivative of first equation, so my first equation is ut plus 8vx equal to 0. If I take derivative of the above equation with respect to t equal to 0. Similarly, my second equation is vt plus 2ux equal to 0, and if I take derivative of the second equation with respect to x, I have vtx equal to 0. So the assumption that we are taking here is the function v, the function v that we are having is continuous. Because it is continuous, we can make the assumption that vtx is equals to vxt, like continuous and differentiable. Once you make this assumption, you can substitute this equation back into your original equation. So vtx is vxt, so this will be minus 2xx, so that will give you I think both of you gave the same answer. So utt is equals to 16uxx. And what is this particular equation? nature of this equation? So there are two things that I want you to understand here, or kind of highlight here, is we have two first order equations, and you can always do something that kind of made it equivalent to one second order equation. And this second order equation, you can use the discriminant analysis and kind of find out which type of equation it is. Yes, if you do the discriminant analysis here, you will get B0 minus 4 times 16 minus 4 times minus 16, which is greater than 0. So this is hyperbolic. But this kind of transformation is not always possible. There are certain kind of equations where you can do this. But what there is another way to do this, which is you start with this matrix C that you already have here, and you compute the eigenvalues for it. If the eigenvalues are turned out to be distinct values, then you can again call it a hyperbolic. Like everything else remains the same. So if you get two distinct eigenvalues, then it is a hyperbolic equation. If the eigenvalues turn out to be like only one unique eigenvalue, then it is a parabolic, and if it turns out to be imaginary, then it is an elliptic equation. So those conclusions remain the same, but that is an alternative way to do it from the matrix A itself, instead of doing all these transformations. So if ever you can calculate eigenvalues for matrix A directly. So if I denote lambda with lambda square minus 8 times 2 equals to 0. So I will get two distinct values for lambda, which is plus or minus 4. So yeah, so since I have two distinct values of lambda, this is again hyperbolic. So both these ways are kind of equivalent in the nature. We'll not go into why, or to give you an intuition, I can tell you like what these eigenvalues are. Just like when we discuss the characteristic lines, when you do a matrix transformation into the eigenvalues and eigenvectors kind of thing, the eigenvectors also represent something very similar to these characteristic lines that we were discussing previously. So it's a kind of transformation. What you're trying to do is moving from x comma t to a different space, and this is something to do with this eigenvalue transformation. You can look into some math textbooks to get a clear understanding of it. But the idea here is either you can convert this into a single second order equation and use whatever discriminant analysis, or you can directly compute the eigenvalues and see if they are real and distinct. If they are real and distinct, it is hyperbolic. If they are equal, it is parabolic. And if they are imaginary, then it is elliptic. So this particular one is hyperbolic. Yeah, the same analysis you can do for this problem also, just to kind of get you practice. So do this one with the eigenvalue one, like do not convert it into a second order one, just do the eigenvalue and see which equation this is. And to kind of give you an intuition of how to relate it with CFT, what does this first equation tell you? What is this first equation in fluid mechanics? Continuity. And what is the second one? Irrotational, but basically what does the second one signify is omega equal to 0. Yeah. So you have a flow where it is divergence free and it is also kind of curl free kind of one. So this is one kind of flow. So what kind of problem is this? What is the nature of the PDEs? The two taken together. Yeah, it's a potential flow. From a CFD, this is actually a potential flow. So what kind of problem a potential flow is? You can identify from determining the eigenvalues for this matrix. So here the matrix will be So what is the matrix now? If I were to start with U, okay, maybe I'll wait for you to solve it. If I write the same matrices as before, this I have U and V. And let's say I want to write an equation of the form where U with respect to X and some constant which we do not know yet, that is the matrix that we are trying to solve, U y equal to 0. This is the form I want to write it in, where Ux is basically the matrix where each of the terms are derivatives. You'll be taking the derivatives for each one. So what is my matrix A? Something like this. One, 0, 0, 1. I already have Ux here. Yeah, I already have the Ux here, so the first term should be 0. So once I have this value, what are the eigenvalues for this matrix? If you were to write the characteristic equation, yeah, imaginary characteristic equation for matrix A, it would be lambda square plus 1 equal to 0, and that will give you plus or minus I, which are imaginary. So this equation is elliptic. And if you recall potential flow is also kind of elliptic. So any changes anywhere kind of have an instantaneous effect everywhere. It doesn't have any time associated with it. It's a steady state equation. Like all the phenomena that we were discussing can be described with this potential flow equation. Yeah, and this is the last problem I have for this. It's also very similar, just that you are asked in a different way. So if beta is real, which kind of equation it follows? Again, just kind of a mathematical one now. I think now you are pretty much clear. So A will be, if I were to define the same as before, the same equation like this, Ux plus AUy equal to 0, what would be the value of my matrix A? Or if you want to define it in some other way to make it easy, it's up to you. Just to make things clear, we'll just let's say I'll define in reverse way just to make things a little easy. Or this is fine. Let's say I write it in the same form. So what would be my A? Can you just check again? So others also got the same answer? Okay, there are two different answers. So first let's start by finding the value of A. So if I were to just expand this equation, what would I be getting? I have something like some matrix where I do not know. So if you were to compare the terms, the one that you gave, this 0 minus 1, if it is minus 1, then I would not get this beta anywhere into that equation. So instead of this A, if you were to kind of write it like a matrix, something like this. Now you can substitute whatever values you have here and then check whether you are getting back the original equation. So your A should be something like the first one, you do not have any uy term in the first equation, so A should be 0, so that part is correct. Now coming to the B part, B is getting multiplied with Vy. Vy has a minus 1, but then Ux is the first term which we do not have any coefficient here, so we have to divide this equation with beta square. So I have to have a minus 1 by beta square. And coming to the second equation, Vx coefficient is 1 and we have the coefficient 1 here, and Uy, the first is getting multiplied with this equation. C term has a minus 1, and Vy we do not have anything, so that will be 0. Should be something like this. So if you substitute this here, first equation has Ux minus 1 by beta square times Vy, which gives you the first equation. The second one is Vx and C is minus 1, Vx minus Uy equal to 0. So this will be the matrix A, and with this matrix you can calculate the eigenvalues. Lambda square minus 1 by beta square equal to 0. This is a characteristic equation which gives me lambda equal to plus or minus 1 by beta, and the problem tells you that beta has a real value. Yeah, since beta has a real value, you can be sure that there are two distinct values, so this is hyperbolic in nature. Are there any questions? Yeah, these are the questions I have for this week. All these problems are taken from previous year exam questions, previous year assignments. To kind of give you a recap of if there are no questions, then I'll just quickly give you a recap and then we'll end the session for this week. So the main idea for this particular week session is to, given a partial differential equation, how do you identify which kind of equation it is? That is the first part of the first objective, is use something called a discriminant, which we obtain from something called a characteristic equation, which helps us to reduce a PDE to ODE. Depending on the discriminant value, we will decide whether it is parabolic, hyperbolic or elliptic. And why do we need that in particular application to CFD is each equation has a different kind of characteristic, the solution has different characteristics, and depending on the solution that we require for our particular physical phenomenon, we will choose the corresponding equation accordingly. So we either have a hyperbolic equation where information propagates in one direction, like the water ripples here. So this has, in the time versus space thing, if you want to observe, there will be two different characteristic lines along, like, which essentially means at any given time the influence of our original distribution will be felt at only given number of points. So there is a finite domain of influence. And then there is a second set of phenomena which we call parabolic equations, where an example is a diffusion like the one shown here, where the effect of the initial disturbance will be felt at multiple points simultaneously. But still there is a finite time for propagation of this, which is usually very less compared to the hyperbolic one, but still there is a direction of propagation here, but the effect of it is actually felt not at just 2 or 3 points, it will be felt infinitely across the entire domain. That is a parabolic equation. And then the third form of equation is an elliptic equation. These refer to phenomenon where the effect of it is instantly felt. There is no time gap between the disturbance and how the disturbance is felt by the other surrounding particles. But what we physically, the instantaneous thing does not happen, but in reality, for example, incompressible flows, we assume that this information propagates at, say, the speed of sound or something, and the actual phenomenon is happening much slower than that. So in the frame of that particular phenomenon, it happens as if the changes are happening instantaneously. So such kind of phenomenon, we use an elliptic equation, and we have solved some problems. All of them are trying to understand the same thing. So given an equation, how do we identify which kind of differential equation it belongs to? And yeah, so are there any questions? Yeah, I guess there are no questions, so I think we can end the session now. So next week we'll be discussing some techniques for finite difference method. We will see what we'll start with Taylor series expansion, which you might already be familiar with, and then develop some equations and understand something called order of accuracy. And from that we'll use a technique. We'll explain you some technique from which you can come up with your own code. Say, if I need this amount of accuracy, what is a finite difference scheme that I have to use, or you will devise with your own accuracy. This many terms I have, so how do I get, say, second order accuracy or third order accuracy? How do you come up with your own finite difference scheme for that? That is something that we'll be discussing next week, and how to use it for a given problem, that we will discuss in next week for different problems. Yeah. So if you do not have any questions, then I think we can end the session for today. Okay, I think there are no further questions. Thank you for joining the session. We'll meet again next week, same time, 5 to 7. And the recorded session will be uploaded on YouTube. You can find that on the website itself.